downward. That also corresponds to the data flow, because you've also asked about integration, integration between these modules. And the data flow is generally downwards through this list. So anyway, starting with the first one, the reliability prediction. Prediction is a historical term used for this style of analysis. A prediction analysis is generally focused on, I'm sorry, was there a question?
No, sorry. No.
Okay. So prediction analysis is a style of analysis that tries to ascertain failure rates for components. Most of the other analysis methods that we'll see use failure rate as an input. It needs to know how often a component fails in order to do modeling of the system level. Finding out that failure rate is sometimes a challenge, and there's a few different ways of getting at it. Reliability prediction is one of those methods. It's a way of quantifying failure rates for components based on how they're being used. They're generally for electronic components, although there's one exception to that. And there's each prediction module or each prediction standard has different sets of equations that calculate a failure rate for components based on the operating conditions and the kind of component it is and the operating conditions where it's being used. Okay. So again, so prediction is based on these standards. Isograph hasn't come up with the calculations for the prediction tool. We're implementing other organizations' standards. There's various different handbooks and standards that have been published, and they're full of dense with equations, and it's a kind of a royal pain to try and go through them by hand to figure out the failure rate for each one of your components. And if you have a bill of materials of 1,000 components, that would take an inordinate amount of time. So what Isograph has done is we've digitized these standards into our tool to assist with coming up with failure rates. So if I select right here, you can see the different standards that we've integrated. MIL 217 is kind of the MIL standard, it's called MIL Handbook 217, is the kind of the original, goes back to the 60s for the original version. Although it's fallen out of favor in recent years because it hasn't been updated since the 90s, and so it's starting to become pessimistic. But it sort of set the table for how these standards work, how these prediction analysis methods work. From there, there's been a number of other organizations that have developed standards for different usages, sometimes different industries, different backgrounds. And so we've integrated a number of them. Telcordia being a popular American standard, IEC being an international standard based on an old French telecommunication standard, GJB being a Chinese standard, SN 29500 is Siemens, that would be a German standard, etc. And FIDES is a new French standard. So we've integrated a number of these different standards in the tool. So let's take a look at it, and we'll use the MIL 217 because again, that's kind of the basis, the introduction standard. So the way it works is we define our components. We have a list of, in this particular example, the computer with different systems to it: a power supply, a CPU board, a display, memory, and display processor. And each one of those is made up of separate electronic components: capacitors, transformer, diodes, resistors, integrated circuits, etc. The way the standard will work is for each one of those component types, it will have a defined equation. Based on the inputs, you run this equation, and it spits out a output, a failure rate output for that component type. So for a capacitor, you will take various properties, such as the environment that the capacitor is working in, the voltage stress ratio of the capacitor, the style, the capacitance, the rated voltage, and it will use all that information to calculate the failure rates. And so here it shows actually the steps: base failure rate for that component type, and then how those different variables influence it. They're called pi factors, which are multiplied by the base failure rate. And it calculates an overall failure rate in terms of failures per million hours. We do that for every single component in our system. So we define for each one of our components in the system, and it will calculate a failure rate, and then just simply sums up the failure rate to calculate a failure rate for our computer system, just shy of 20 failures per million hours. Okay. So again, that's what the standards will do, is they'll calculate the failure rate for a component based off its use, based off its variables. The software, Isograph's prediction module, has just digitized that. So rather than you having to solve that equation by hand or programming Excel to calculate it yourself, we've already integrated all those calculations. Now it's kind of annoying to build it all by hand. So we do have a sophisticated import feature. We can import, say, from an Excel file. So if you have a bill of materials in Excel, you can import and have a lot of this data be read in and automatically set through that import feature. So it kind of cuts down on the amount of work you have to do. You don't necessarily have to, it would be kind of time consuming to manually create each one of these components and manually enter each one of these parameters. So we have a number of ways to speed that up, the import being one of them. You can also set default values as well. So for instance, at the block level, this power supply right here, I can set default values that will be pre-populated for its subcomponents. Anyway, through all of that, we'll be able to calculate a failure rate for the system, but mainly what we're after is the failure rate for the components, right? The system failure rate is a simple roll-up. It sums up the failure rate, and that oftentimes doesn't really capture the full logical complexity of a system. We'll talk about that a little bit later in some of the other analysis methods, where we have more logical complexity, such as redundant systems, backups, and things like that. So again, the prediction is mainly focused on calculating the failure rates, and then we might use these in another analysis method. We'll come back to that and talk about how to use these failure rates and some of the other analysis methods in a little bit. Once we start looking through those methods, I'll show how to transfer the failure rates. But before we get that, are there any questions so far on the prediction? Anything you'd like to see in the prediction module?
So with the parameter profile, is that how you select the different stress parameter and you see a graph?
Right, yeah. So what's going on over here on the graph on the right-hand side? Again, this graph on the right-hand side is customizable. You can show different plots. You can show different plot options, but the default one that's just being shown right now is for whatever I currently have selected. It will show how the failure rate changes. Right now, it's with respect to the temperature as my x-axis. So
you can change that to voltage and
right,
whatever.
Yeah. So I could change my my x-axis, either temperature or electrical stress, are my two options for what I can set to the x-axis. So what this will show me is it'll help me figure out what the operating temperature should be for my system. So I can see that it's relatively flat failure rate until I'm getting up to about 60, 70 degrees Celsius, and my failure rate will start to take off. And so that tells me I don't want to run it too hot. What's too hot? I can look at the failure rate, figure out how hot I can run it to meet that given failure rate. You can do, again, a similar thing. This is for the system level. You can look for individual components, and you can also do it based off of electrical stress of the components. Right.
Are all those curves defined in the standards, or do we have to add those in on a component-by-component basis as we build the model?
This curve here is based on the standards calculations. So one of the inputs, well, two of the inputs, one is the voltage stress and the other is the temperature. Those are both inputs into the failure rate calculation. So the temperature goes into the temperature pi factor, and the stress goes into the stress pi factor. Right. So changing those values will change these pi factors and therefore change the overall failure rate. So the way this graph is calculated. So, sorry, go ahead.
I was just going to say, it'll keep all the other parameters constant. And then
right, exactly.
Just adjust.
Yeah, it changes that one parameter to see how it affects the overall result. Okay. Any questions on that? Any other questions, I should say? Clint or Brett, is there anything else you'd like me to show in the prediction module, or shall we move on and talk about FMECA?
No, I think we're good on that.
Yeah, and of course there's all sorts of little features and helpful things that you can do, special functions to globally change environments and temperatures and stress if you want to try different values. And there's lots of features to the tool, but a lot of them are just too detailed for what I want to get into on a basic overview. In a more thorough training session on the tool, I'd show off every little feature that you have. But for now, I just want you to get a basic overview of what the tool does and how you use it. Okay. So let's move on to the FMECA module, going down that list. FMECA, and I'll open a different example file for this one. Save project changes, no. I'll go to my FMECA example. And this is a very similar computer system. It's a little bit simplified from that last example I had. but it's very similar. I have the same power supply, CPU board, and memory unit, although it's a little bit simpler in this case. Now, to explain what FMECA is, it's actually really three different analysis methods. FMECA, FMEA, and FMEDA, FMEDA, are three similar related styles of analysis. The term, in case you're not familiar with it, FMECA is failure modes, effects, and criticality analysis. FMEA is or FMEA is failure modes and effects analysis. And FMEDA is failure modes, effects, and diagnostic analysis. We'll start with, say, FMEA. Actually, I think I have a separate FMEA example. Where's my FMEA? SAE. There we go. Oh, that's a little bit too simple. I'm going to go back to my other one. This one I can show off how the FMEA works. So the FMEA is we'll start there because that's kind of the simplest. It's the most qualitative. So prediction, we're looking at the failure rate, how failure rates of components cause failures of the system and the overall failure rates. In the FMEA, we're looking not just at the failures of a component. So say, for instance, this capacitor fails, and that fails the power supply and then therefore the computer system, which is how it works in prediction. But in FMEA, we're looking not just that the capacitor has failed, but on its specific failure mode. So a capacitor can fail in different ways. So for this one, I've defined 4 different failure modes for the capacitor. It can either short out, it can have a change of value, it can be an electrical open failure mode, or it can be an other failure mode. And depending on that failure mode, that can have different impacts on the system. The system can fail in different ways, and some of those failures, system failures, are worse than others. So the failure of the capacitor could produce different effects on the system depending on which failure mode. So the point of all the FMEA methods, FMEA, FMECA, FMEDA, is to figure out not only how the components fail and their impact on the system, but rank those failure modes to figure out which have the worst impact on the system. So again, we'll look at different ways of doing that. The different.
Where
sure,
are the rates derived from standards, or do you have to input those?
So we'll start with FMEA, and that won't use failure rates. When we get into FMECA, it will use failure rates. Those can be either input directly, or they can be imported from the prediction module. So in this case, I'll most likely import them from prediction, and I'll show how to do that in just a little bit. Okay. So let's start with an FMEA. So I'll go to my project options, and I'm going to change my prediction my FMEA standard.
Yeah.
Go
Hello.
ahead. Yeah, sorry.
I have a question. So for your component failure mode, like the capacitor, where did you get that information from?
For the failure modes?
Yes, for the electronic component, for example, in this case, the capacitor.
Yeah, so the capacitor failure modes, that would come from either from experience, it could come from a library, it could come from a data sheet, it could come from any number of sources. There is one library built in, the FMD, the failure modes database. That's primarily for non-electronic components, so for capacitors. There's one library of failure modes built into the software.
If I want to modify the failure mode with this tool, does that have that feature or option?
Sorry, I'm having a hard time understanding you. Are you asking if you can modify the failure mode?
Yes, if I want to modify the failure mode, for example, let's say I want to take out some of the failure modes in like capacitor change or order from this list, can I do that with this tool?
Well, yeah, of course. Of course. Nothing here is set in stone. This was all this data was user entered, right? So this whole hierarchy on the left-hand side, the block hierarchy, the failure modes for each component, those are all user entered. So you can enter whatever information you want. You can delete information. You can change information. Nothing here is fixed.
This is just an example.
Yeah. Can you just build an example, like from scratch, very simple, like RLC circuitry?
Oh, just
like
to show how to build the hierarchy and how to add data? Sure. Okay, yeah, I'll come back to this and talk a little bit more about the methods in a little bit. But for now, we'll just go to the build from scratch. So to create the hierarchy, I have buttons up here to add blocks. So I can add a block representing my different components. That I have, if I was building that one, I had my power supply, right? So I can have my power supply. I had another one representing my memory units, etc. And then I'll have the child blocks for that power supply. So I had, say, a capacitor. And of course, I could enter a failure rate. Right now, I'm not. That failure rate.
What about failure? What about mode distribution percentage? Does that have the feature for that?
One of the modes.
Because each component failure mode has a distribution percentage, like 20% open, 10% short, 20% order. That are all.
Right, that's called the apportionment. That's called the apportionment. Yes. I haven't gotten to that point. Yeah. So if I have a capacitor and I have a resistor. Okay, and then for each component, I would add its failure mode. So one of the failure modes of a capacitor, I'd click to add a failure mode and describe that failure mode. So I had what, shorted electrical?
No, just a short. That's one.
Okay.
Shorted
and then the
open.
apportionment is what percentage of failures of the capacitor are due to this particular failure mode. So I could say my shorted electrical represents, say, 60% of my faults of the capacitor. So I can select OK. And so now I've added that one. I can continue to add failure modes for the capacitor. So what else did I have? I had change of value. And let's say maybe 15 or so of the percent of the faults, or actually let me think about this. 25, let's say 25% of faults are change of value. Okay. But I can continue to add the different failure modes for the capacitor.
Thank you.
Open electrical was the other one. Let's say that's 10% of faults. And then the final one, let's say, is other. And that was, let's say that's 5% of faults. So I'm just trying to make sure that they, let me change the view down here so it shows the apportionments. I'm trying to make sure they sum to 100%, which I can almost sum up to, 60, 85, 95, 100, yeah. So I want to make sure I account for all faults. Now, granted, all my capacitors will probably have those same failure modes, so rather than defining each one individually, I can create an apportionments library and predefine, this could be imported as well, I could predefine the types of components that I'm going to have and the failure mode. So I could create a capacitor in my failure modes library and then predefine those failure modes and their apportionments.
You said there was going to be a built-in library. Does that include a apportionment library component, or just
so the built-in library doesn't use this apportionments. It's essentially the same thing. It doesn't use this particular feature, but it does have the failure modes with their apportionments built in. But it's not through what we call the apportionment library. It's doing the same thing, but in a different way. Right, so once I've added in all the failure modes, click OK to add that to my apportionments library. And now when I want to add a capacitor to my, I've added it. Now if I want to add a capacitor to my project, rather than using this option, I use the add apportioned block. Let's say under the memory unit, I have a capacitor. So I click add apportioned block, I select that capacitor, it imports it, and it has all its failure modes already filled out. So I don't have to redefine that for every single component. Now, so the next part of FMECA/FMEA analysis is once we've defined the failure modes, we have to define the effects of those failure modes. What are the effects? Generally, those effects propagate upwards through the hierarchy. So what's the effect of that shorted electrical failure mode on the power supply? So what I would do is I'd go to the effects tab right here and add an effect on the power supply. So what's the effect on the power supply for shorted electrical? It might be loss of function or something like that. Okay. I'll add that as an immediate effect. Okay. Now that effect, so now it says effect is defined, that effect becomes a failure mode for the power supply. See, for the power supply, now it has a loss of function failure mode, which is contributed to by the capacitor's failure mode. That effect for the power supply itself would then have an effect on the system level. What's the effect on the computer system for the loss of function in the power supply? System failure, for instance. Okay. So select OK. Select OK again. And so now at the system level, I have a system level failure mode called system failure. At the system level mode, I will also define severities. I can define severities. There's one of the FMECA standards is MIL 1629, which defines 4 severities, ranked 1 through 4. Catastrophic, critical, major, and minor. So maybe this is a catastrophic, or excuse me, a critical failure, because it represents a loss of system. And those are weighted, I think, weight of 10. The way they weight them is how bad is it. Catastrophic is 100, critical is 10, major is 1, and minor is also 1. And those values are used to calculate the risk level with each failure mode. Okay. So I've calculated that, and then that severity propagates downwards to the failure modes that contributed to it. So when I run the analysis, this failure mode is assigned a severity of severity right to the critical severity, because that's the end effect to which it contributes. Okay. Before I run the analysis, this really isn't a completed example, so let me go back to my other example that was a little more filled out with data. So I could apt up this process, I'd get something like this. Each failure mode contributes to an end effect. So this shorted electrical, the immediate effect is an incorrect meter reading, right here. The immediate effect of this is a negligible effect for small changes at the system level. And that has a severity of rank 4, minor. It's the lowest possible severity. When I run the analysis, it will calculate a criticality for each failure mode. That criticality is based off of the failure rate of the components, the operating time factor of the components, the apportionment of the failure mode, the beta factor is the % chance that the failure produces the effect, and then the severity of the end effect. And so at the very end, do I have it shown here? No, so I think I have a separate. There we go. For each failure mode, it will show me the mode failure rate, the mode criticality, and the mode risk contribution. This helps me identify which failure modes have the highest risk. Okay. And again, this is an example of what's called a hardware FMECA. So hardware level is two ways of building the hierarchy. Here I'm listing individual components. Some FMECAs are built based on the functions of the system. You look at each subsystem as like a black box that provides some function to the system. And rather than considering individual hardware faults, we consider the loss of the functions of those devices. And so we might look at a higher level and just look at the functions of the power supply rather than the individual hardware components in the power supply. So there's two different methods of building a FMECA. It's the hardware approach and the functional approach. And the software supports both of them. And again, this is a FMECA, which is a highly quantitative method where we calculate the risk contribution. Another frequently used method would be a FMEA, which is a more qualitative method of ranking the failure modes. Just change this over to FMEA. And the way a FMEA works is, again, the hierarchy will be generally the same, the failure modes will be generally the same, and the effects, that's all defined the same way. FMEA is a different way of ranking failure modes. Rather than doing this highly quantitative, entering a failure rate and an apportionment value, sometimes those values are hard to come across. So sometimes people will use a 1 to 10 scale on a few different measures. So rather than trying to come up with a failure rate, they'll have an occurrence ranking, which is a 1 to 10 scale, a detectability ranking, again 1 to 10, and a severity of the end effect to which it contributes. Again, that's 1 to 10. We multiply those three values together to get what's called the RPN, the risk priority number. And then we can examine the risk priority numbers of all our failure modes to figure out which failure modes are the highest risk. So that's the way a FMEA would work. Okay. Any questions so far on the FMECA?
It might be something that comes up in the next bit, but are you able to link your failure rates from your FMEA into the bottom level events of a fault tree?
Yeah, well, yeah, that's we'll get to that when we look at the fault tree. Yeah, we'll show the data linking, and actually I'll show that from the prediction. So you can enter the failure rates in the FMECA. You can also enter the failure rates in the prediction, and they can come to the FMECA. Let me just show that first part, and it'll be a sort of a precursor to showing the FMECA to fault tree link as well. Let me go back to that prediction example that I had earlier, my MIL217 model. So here I've calculated the failure rates. Now suppose we want to go through and add the failure modes for these blocks. What I can do, there's a function to convert the prediction hierarchy to a FMECA. What's more is when I do that, make sure everything's set the way I want it to be. My units of failures per million hours. Let me make sure my FMECA is set correctly in terms of failures per millions of hours. Oh, well, make sure that's set. And then I also want to turn on an option through my data linking to assign data link on intermodule copy. So that what I'm going to do is I'm going to convert my prediction project to the FMECA, prediction hierarchy to FMECA. It's going to give me a confirmation dialog. Are you sure you want to do that? I say yes. So it creates that entire computer system within my FMECA. And what's more is it copied the calculated failure rates from the prediction and data linked them back to the prediction such that if I change the prediction, I can automatically update the failure rates in the FMECA, failure rates from the prediction. And this will work in the same way going FMECA to fault tree as well, or prediction to fault tree. We can copy these failure rates into the fault tree and data link them, such as if we change the source data, we'll change the target as well. Okay, so once I've done this, now the only other thing that I'd have left to do would be to add the failure modes. If I've created an apportionments library, there's an option to auto-add apportioned failure modes, right? Or any block that has a description matching a block or matching an item in the apportionments library will automatically add the failure modes. Now I don't have my apportionments library defined in this project file. Well, I can't do that here. What's more actually is when you do that conversion, it automatically adds the apportioned failure modes, the apportioned failure modes if it finds descriptions of blocks from my prediction that match descriptions from my apportionments library. Okay. Any other questions on the FMECA module?
Nope, I think we're good.
Okay. So going down the list, the next ones would be RBD and FaultTree. We'll talk about them sort of simultaneously or together because they're both very closely related to each other. RBDs and FaultTrees are both analytical systems analysis methods. They use the same mathematical models to solve the system. Really, the main difference between the two is the diagram format. RBDs are more like a process flow. It looks a little more like a flow chart. Makes a lot of sense when you're trying to build based off of a process availability schematic. When you're modeling a process and you want to build a diagram to model the availability of that process. Fault trees are more of a top-down root cause analysis method. They're more frequently used in safety analysis, root cause analysis when we're examining a fault, a system fault, trying to figure out what could lead to that fault occurring. It's kind of a deductive reasoning approach to solving the fault tree, or to solving the system. Again, the mathematical underpinnings between the two are the same. I'll show each one in turn just to show the difference in how they're used. Keep in mind that both of them can be data linked and both of them can be created from the FMECA or the prediction. Both options, you have the option to convert from FMECA to RBD, FMECA to FaultTree, prediction to RBD, prediction to FaultTree. Okay, we'll start with the RBD. Do I have no, I don't have one. I have a system block already defined in this project. So the way that you'd build an RBD, we just start from scratch. You'd start by defining a system, right? So now I have a system block. And then I can just simply use the toolbar buttons for adding blocks, adding nodes, and adding connections. So the add block, and then I can click around to create some logical structure. They can draw connections, hook them all up to each other. Right, touch. You can also expand on them. So maybe this one block here represents an entire subsystem. I can really drill down, I can go page down, draw a subsystem for this block. So maybe it has a parallel arrangement. Let you drop in a couple nodes to start and end, and add in some connectors. Right. We'll talk about the quantitative inputs to these blocks in a little bit when we get to the fault tree as well, since this quantitative inputs are the same in the RBDs and the fault trees. I will mention that each one of these blocks, you can edit it. If I double click on it, I can edit it to be able to change things like its ID, its description, its appearance, add some notes, hyperlink it to another item, to another document or a web page. A lot of these same options will appear in the fault tree as well. Okay, so there's lots of properties I can set for the RBD. That RBD can also be automatically created, either from the prediction or from the FMECA. I'll actually show, I do convert prediction hierarchy to RBD. Sure? Yes. So what it is just creates a serial model from the prediction. So I have the power supply, the CPU board, and the display, and then each one of those is a series arrangement of all the components coming from the prediction model. I could then go through, since prediction is a very logically simple method, everything is assumed to be single point fault, I could then go through in the RBD and rearrange things, maybe add in redundancies. For instance, I could maybe say this isn't the correct arrangement, maybe these are supposed to be redundant to each other. It actually doesn't make sense in this particular example. But I could redraw the blocks once I've converted them from the prediction to tackle the actual logical arrangements of the system. Okay, and again, a similar thing can be done in the fault tree. In this case, I'll open up my FMECA so I can show converting from FMECA to the fault tree, and it works again the same way as the RBD. Let's jump over to the fault tree. Collapse all that. First, I'll show how to build a fault tree. So again, I selected fault tree from the module selector. To build the fault tree, I have toolbar buttons, just like I did for the RBD. Except rather than adding a system, it's adding a top gates. And then rather than adding blocks and connections, it's gates and basic events. So I click the Add Gate button, and now I can click to add gates underneath wherever I click, whatever gate I click on. I can add some gates underneath it. Right, and then I can click to add events in the same way. Click to add an event. A couple goes here, one, a couple more there, and say a few under there as well. You'll notice they all default to OR gates. Well, with no inputs, it's going to be, it shows a transfer in symbol. With one input, it shows what's called a null or a pass-through symbol. With multiple inputs, all the gates default to OR, although we can change that. I go to clear add mode, then I can go and edit the gates, and double-click on the gates to change the symbol type. So for instance, change that to an AND gate, or say this one could be a vote gate. Change the symbol types for all the gates. Okay. Just like we could paginate in an RBD by drilling down beneath a block, we can paginate in the fault tree as well. If we're dealing with a very large fault tree schematic, it might not fit that nicely all on one screen, so I can paginate to break it across in smaller chunks. That's easier to work with. This also applies to the printouts. When I'm printing out a report of my fault tree diagram, it will be paginated in the report based off of the page gates in the tree. The basic events in the fault tree look a lot like the blocks, the component blocks in the RBD. If I double click on it, you'll see a lot of the same options. Things for the ID and the description, the appearance options, notes and hyperlink options are all the same between the RBD and the fault tree. Also have options for creating the failure data, the failure model. This is where we input that quantitative failure inputs. We can create a new local failure model to be able to directly enter failure data. Now, there's 18 different failure model types, depending on the types of failure data and failure characteristics for this component. So maybe the component represents a conditional fault. There's or a probability of failure on demand. So I might enter a fixed probability of failure. Or maybe I have an MTTF and an MTTR for this component. Maybe, so I use the MTTF model. Maybe the component has dormant or hidden faults, so I use the dormant model and I specify a test interval. How often do we check it to make sure it's still working? Or in aerospace, they might use a time at risk. In process safety, they have their own separate failure model. So there's different failure models to handle the different types of data that I would have and the failure characteristics of the component. Okay. So that's what all these different failure models represent. And whichever one I choose, I would enter the corresponding failure data. As I mentioned earlier, this data can be imported from the prediction from the FMECA. And then again, it uses the same data linking options. Let me set up, redefine my my settings. Data links, assign that data link. I can set how I want it to work, include the failure modes, right? Or if I just want it to be based on the hierarchy, or if I want to be based on the failure modes themselves. So let's select OK. Now when I do that conversion option, FMECA hierarchy to FaultTree, again, it gives me a confirmation. Yep. And it will create a new FaultTree, XYZ computer system. And it puts everything all on one page. So I'd want to go through and change this. It's awfully wide. It shows the computer system, the end effects for the computer system. So intermittent operation was one of them. It was one of the end effects from the FMECA. Negligible effect for small changes. The no effect. And the catastrophic and no operation. And then for each one of those end effects, it breaks it down further into the power supply failures that lead to the negligible effect, CPU board failures that lead to it, breaking it down to the individual components and component failure modes that lead to those higher level failure modes. Each one of these basic events representing the component failure modes will have a failure model automatically created and data linked, so the data link is active, reading the failure rate from the FMECA, pre-populating it in the FaultTree basic event.
And just to clarify, all these data links will keep updated as the other, as the reliability model changes, or if the...
Yeah. So what I do to keep it updated is I use the edit transfer linked data option, and that will update the FaultTree data, make a change in the FMECA. The reason that we have it in the menu option. Oh, go ahead. Sorry.
No, sorry. Is it just the values associated with each item that will keep updated?
Yes.
Or if you add a new item to one file or the other, will it auto-populate new bubbles to the other analyses?
It's just the data, just the values. We want it so you can change one independently of the other, because now I might go through and change the fault tree, right? Change the structure, change the gate types, maybe add redundancies. So we want you to be able to change the structures independently. Maybe I'm not interested in one of these, so I want to be able to remove it from the fault tree. So it's only the failure rates, only the input quantitative data for the basic events that's data linked back to the original. I can easily add an additional item. So suppose I added a new item in the FMECA. Say we added another RAM board. So I'd say copy and then paste to add a new one. So now we have an additional item with all its components as well. And now I want to add these into the fault tree. I can also just copy and paste from here and then take that over to the fault tree and then pick one of my gates. You just put it under the top and select paste, and it will add, it showed way off to the right, all those other items in the new item that I added in.
Will it recognize that the top level effects are the same as the top level effects that have already been pasted in there, or do those links have to be remade?
So I would probably paste it into the, since I did a functional, or the failure mode hierarchy rather than the block hierarchy, I'd have to paste it into the individual end effects. So this is the tree for that one particular end effect. So in this case, it would be a little bit trickier to get everything synced in, right? It makes a little more sense just to paste in a new item when I'm doing it based on the block hierarchy rather than the failure mode hierarchy, because the failure mode hierarchy splits up the blocks. So, yeah, so it would make a little more sense if I'm doing the block hierarchy than the failure mode hierarchy.
If I can just interject, it looks like we're pushing up on 2 o'clock here in Utah. Joe, how are you for time? And Christina and your team, how are you guys doing for time right now?
I'm good to continue on for a little while longer. There's extra.
Yeah, I reserved for 1 more hour, but I think we should. A lot of people need to leave in half an hour, so we should.
I have a question regarding your FaultTree. If you don't mind. So how do you address common mode failures?
There's some crinkling going on. Can we?
Can you hear me now?
Yeah, I can hear you.
Can you hear me now? Can you hear me now?
Yes.
Yeah. So how do you address common mode failure in your FaultTree? Do you indicate that by some type of color indication?
One more time, could you repeat that? To indicate what?
How do you address or indicate common mode failures?
Okay, common cause failures. So a few different ways of handling common mode or common cause failures. This one's a little hard to see. So the main issue, another example I have. Okay. So in this particular one, we have a common mode failure. This board-based supply common cause. You can see that because of the ID. Right. The same thing here. This is also a common cause, and again, you can see that based off of the ID of this item. So how do we address that? The best way to do it, again, it's not done automatically by the software. The best thing to do is when you know you have a common cause failure is to color code it. You can change the color of one of those items. So that red, so you get stand out. And it will color code, since it appears in 2 places, it colors it in the other place as well. So when you create this common mode failure, this common cause failure, I'd use the copy and paste options, copy and paste. So when I do that with an item, I say, ooh, now I have a common cause. So I should color code it to indicate it to it. The program doesn't really automatically do it, although there could be a customization that could be added for that. I think I might have.
When you run the top level of FaultTree, are you going to run the cut sets and see the...
Exactly. So the way this is calculated when I run it is it, so this is already up to date. When I run the analysis, the cut set analysis, so this is a FaultTree in and of itself, right? So, but it calculates that this is a common mode when it's doing the Boolean algebra to calculate the cut sets. So it's taking into account that both branches of this gate here have a common cause. So I can actually see that one of these failure modes, say contact breaker 1 failure and transformer 2 failure. I can see how that affects it through the common causes. So I can trace it down to the individual basic events. Contact breaker 1 and the transformer 2 cause the failure of the electric port A. And that affects both instances of it, right? So it would cause the loss of cooling to the heat exchanger.
Okay, one more question. How easy it is to use to reuse an intermediate gate? So, like example, you copy the intermediate gate name, and you want to reuse it for another. Instead of retyping the gate and all the attributes, you can just copy and paste.
Yeah. So for the intermediate gates, any item, gate, or events, you can use copy and paste. Copy and paste. So you use that same thing in another case. So that's what I've done with this loss of board A supply. I just selected copy, and then I can put it anywhere else. I can select another gate, say paste.
Can you demonstrate that? Okay, very good. Okay, good. Okay, very good.
You can do that for events as well. There's also a second paste option, a paste special, which will create a new item with similar properties to the old one. If I have another electrical system, it's very similar to this one here, but is actually a separate, distinct system, I can use the copy and paste special to create a new item with similar properties as an existing item.
Okay, very good. Thank you.
So Joe, why don't we take another 15 minutes with your permission and cover any last things. I think that they wanted to talk about Weibull as well. And so if we can cover that, and again, if this is something that was useful for you today and we need to schedule another webinar, we can certainly coordinate this again. I just want to be cognizant of everyone's time here. And anything else you wanted to see on FaultTree before we moved on from there?
Venkatam, is there anything that you want to say?
Yeah, all my questions answered actually. Different people asked. So I am fine right now.
Okay, so I didn't quite catch that. So were there any additional questions on the FaultTree Plus, or did I answer them already?
We're good here.
Yeah. Hey, this is just meant to be an introduction to help you get started, and I'm sure that once we get done, you'll have other questions that come up, and that's totally okay. If you want to pass those one-off questions to me, or just set up a different time, we can do that.
One question that I have before we start on the Weibull is all those FMEA, FaultTree, when we have this license, and we have all the modules, do we have to install like in one computer with everything, or is it web-based? How are we going to be talking to all these different modules?
So licensing is, firstly, as mentioned, it's a la carte to purchase the licenses for the modules that you need. So if you want, say, prediction, FMECA, RBD, and FaultTree, so if you want basically everything, that would get you all the way down to Weibull, because the FaultTree license includes event tree, markup, and Weibull. We support two different license methods, standalone or node locked, where you put them on one computer, and then anybody using that computer can use the license and use the software. We also support floating network licenses, where you can designate a licensed server on your computer network. So you'd set up one of your servers you could use as a licensed server, and that can host the licenses. The advantage of doing a licensed server that allows for floating licenses, you have a pool, and any user on your network who has the software can check out a license. So you could have more active users, or you could have more users than you have available licenses. Just only a certain number can use the software at a time. So I want 5 people to have access to the software, but only 2 licenses, and so only 2 people have them at a time. And again, those licenses work on the same per module basis. So maybe we get 2 licenses for everything. One person is using prediction, so they only need to check out a prediction license. Someone wants to use prediction and FMECA, so they check out the second prediction license and 1 FMECA license. Someone else only wants to use FaultTree right now, so they can just check out the FaultTree license. So it's when you start up the program, you check out which modules you want to use. So if you don't want to use one of the modules, you don't have to check it out, and that license remains available in the pool for other users who might want to use that module.
Okay, thanks. You can go ahead and, Greg, do you want to introduce yourself?
Oh, hi. Sorry about being late. I had another thing to attend. But I'm Russell Kibicek. I'm the manager of the group. So I assume you guys are pretty close to the end of the demo, or you're only halfway through? Oh,
We're
close
most
to
of the
the
way
end.
through it. We're most of the way
Okay.
through it.
One thing,
So,
this is
continue
Brett.
on.
Oh, sorry. I was just going to let you know I am recording this. So what I'll do is I'll actually save the link and then I'll send it out. So anyone that came in a little bit later, whatever, you'll be able to rewatch that at your leisure.
Thank you.
Good, you can continue on. Are you gonna start with the Weibull now?
Yeah.
Okay, if you can, Weibull.
Sure, the Weibull module. Okay, so the Weibull module can be used on its own, but it's most likely used in support of either the RBD or the FaultTree. What the Weibull module is used for is it's another way of obtaining failure data to quantify one another analyses. So I mentioned prediction is one way of quantifying components, figuring out the failure rates used for components. And then we often use those failure rates from the prediction in, say, an RBD or a fault tree, so that, because that's one of the required inputs to a fault tree is the basic event failure rates. Another way of coming up with those failure rates of the fault tree would be the Weibull module. While prediction is generally for electronic components, the Weibull, we can use it for any component type, but it's also based on real-world historical data. What we usually use is something like a work order history, or something where we've recorded failures for a component. So in this example, I have two cases, or two examples. I have a fan motor and a set of valves. So what I did is I recorded that valve whenever I had a whole bunch of them operating over a number of, over time. Every single time one failed, I recorded it. How many operating hours did I get out of that component before it failed? And that's a plot. I can, excuse me, if I go to the grid, I can show those time values. So there's just a list of time values. One valve lasted 25,634 hours before failure. Another valve lasted 14,637 hours. Third valve lasted 9,351 hours. So each one of these represents a failure time for a valve. So I recorded how long each one lasted before it failed. And then I input that. Of course, I didn't type these in one by one. These were imported from an Excel spreadsheet. Right? Those are imported in. And what the program will do is we'll plot those red points represent each one of the failure points. The x-axis is the time. The y-axis is the reliability. It has a method and algorithm for calculating reliability based on the total number of operating hours, the total number of failure points, and all that. And then we can match a curve to that data. There's a few different curves we can choose from. I've chosen a 2-parameter Weibull distribution to match to this data. And the program automatically calculates the Weibull parameters, the characteristic life of 12,390 hours, and the shape. Shape 2.168 means that the component failure rate, or the component is wearing out. The failure rate is increasing the older the component gets. It gives a few other values for how well does this line fit the data. 97% correlation with 4.5% error means a pretty good fit to the data. Right, so that's what some people might stop there. They're just interested in finding out, like for a given component, the characteristic life of that component. But what we could then do is use this to support a fault tree analysis. I jump back into the fault tree. What I've done is I've created my fault tree, added that valve basic event, and then from its failure model, oops, I haven't attached the failure model. Let's attach the valve failure model. Okay, look at that. What I've done is I've chosen the Weibull model type and then linked it to that valve's data set. So now the failure parameters for the fault tree basic events are inherited from that Weibull data set. In other words, now this fault tree, this basic event's failure rate is being quantified from real-world historical failures for that component type. Make sense?
So Christina, quick question. At Progress Rail, do you have a lot of that data for your different components, or is this particular model something that you're already using?
Yes. So we use Weibull right now with ReliaSoft through ReliaSoft software.
Perfect. So you're familiar with what this is and how it works.
Yep.
So just checking in, we've covered the prediction model, we've covered FMECA, we've covered RBDs, FaultTree, Weibull. I think the last piece was the reliability growth. Is there something specifically with reliability growth you wanted to see?
Well, I think we covered basically what we want, the prediction FMEA, FaultTree, then Weibull.
But what type of reliability growth function do they have in the tool?
Then,
Okay.
Yes, please go into it.
Yeah.
You lead the conversation.
I should
Well, not lead it, but what you're looking for.
Yeah, I mean, it just sounds interesting. I would like to see if you can demonstrate what type of reliability growth aspects does your tool perform, or functions does your tool perform.
Okay, so the reliability growth module in the tools. Reliability growth is a specific analysis type. It's an analysis focused on figuring out if recent changes that we've made are having a positive or negative or no benefits on the system. So it's like Weibull in that it's based on historical data. So in this particular example here, we see something that looks very much like that Weibull curve, where we have red dots which represent failure times, and then a curve or a line matched to them. Now, whereas Weibull, we're only just trying to quantify an overall failure rate. In growth, we're looking for a trend in failure rates with the more recent failure times versus the older failure times. What we're asking is, it's usually based on some change. We made some change to maybe our maintenance policy. Maybe we've bought a more reliable component. We've made some design change to the component, and we want to see, is this having a positive, a negative, or no impact on the system. So we've plotted all our historical failure times on the plots, and based on over the time, what it's looking for is there evidence of reliability growth. So again, it gives, like the Weibull, it gives two parameters, a life and shape parameter, which are given right here, and then it gives a couple of statistical tests for growth. So it gives a critical value, there's a statistical test, and this is all based on an IEC standard that shows how the equations to calculate these. It calculates the U test statistic, compares that to a critical value to determine whether or not there's evidence of positive growth. In this particular data set, we say yes, there's evidence of positive growth. What that means is that the failure rate is going down, or the MTTF is going up with the later failure points. The more recent failure points have longer times to failure or lower failure rates. Then it also does another goodness of fit test to make sure that the model fits the data. So in this particular example here, it's hard to interpret it just from the graph here. The graph is mainly just showing the data points. What we're really looking for is this section right here. This is showing us that there's evidence of positive reliability growth. Now, there's different ways of running the reliability growth for different types of data that we might have, but they're all focused generally on the same thing. The recent changes that we've made to our system, are they having positive benefits in reducing the failure rate of the system?
Excuse me?
Yes?
I have a question. I'm not familiar with this module, but can you use the same data that we have done for the Weibull and then do the reliability growth? Just to see, because usually reliability, from the graphs that I see, is more like when you have intervention. Can you use the same data and then see the difference when you have a Weibull analysis and when you do the reliability growth? Or
well, this one's estimating a beta slope. So I guess are you able to plot a previous Weibull and then uses what this one predicts, and then do a side-by-side comparison on
You want to compare two different populations, or N populations, right?
Yeah, that's true.
So Weibull and growth are really two different analyses focused on two different outcomes. So the Weibull, we're trying to take the population, figure out failure rates so that we can use it in the fault tree. In the growth, we're taking a population and looking for a trend, upwards or downwards trend with regard to a recent change. If we have made a recent change and we think there's going to be a change in the failure rate, I probably wouldn't want to use that data in Weibull, because the Weibull is used to support a fault tree. And for the fault tree analysis, I'd want like a failure rate for the way things are now. I wouldn't want to use old, out-of-date data. So I probably wouldn't want to do this. I mean, you could import the same data. You could take the same Excel spreadsheet, import it to both Weibull and to the reliability growth. But the two modules are used for different end goals. So there is no facility to compare them side by side or anything like that.
I'm having difficulty looking at the reliability growth chart and seeing the difference in the populations. So one population, old design, old components. Then I make a change, and I've got new design, new component, and it's got a different curve to it. How do I'm not seeing that in this image.
Right. So this one is, as I mentioned, it's hard to see it.
There's different axes.
This is just showing a log plot of the time and the number of failures over time. So from this on its own, it'd be really hard to see. There's another plot that you might be looking for for failure intensity over time, and here we can see a clear trend in the failure intensity. We can see that that's going down over time, or the mean time to failure. Same mean time to failure is going up over time.
That's a calendar time, not necessarily a unit run time.
It depends on how you input your data.
Yeah, it's based on
your data. Your independent axis will be defined by your input.
Okay, thank you. Is there anything else?
Well, I want to thank all of you for taking some time with us today. I just wanted to follow up with, are there any looming larger questions outside of the modules you had about Isograph at this point, or anything that plaguing you still about what Joe showed you today?
Okay, clear. I think
Like we're pretty good.